This is state space representation exercise. So below is the state space representation general structure. This is not in a controlled canonical, observable canonical, nor diagonal canonical form. It is in a different form. On the other hand, this one is in the controlled canonical form, as evident from B having only the one on the top as occupied. The rest are zeros. For the phase variable form, it follows a command directly from, or rather a series of commands directly from the controlled canonical form. For the LTI object representation, this will convert the given to a transfer function. So this transfer function can then be directly converted to a state space using the SS command. So this displays A, B, C, and D, which are the state matrices. Notice that for A, there is a bit of a difference regarding the results as compared to initially from A, B, C, D, despite using the same set of numbers. So by plugging the ABCD instead to an SS to TF command first, displaying the numerator and denominator, and then converting that to a TF using the TF command, this provides more of an accurate reading, as displayed from the numerator matrix, the 24 is correctly displayed, and from the denominator, the 9, 26, and 24 are displayed. And so, by using the SS command, we can see that the negative 9, negative 26, and negative 24 in the denominator was displayed correctly. So, that means it is better to convert this first to the coefficients of the transfer function before you put this to the state space. Polynomial form, by using the polynomial, the TF command, from the state space representation will display the transfer function. So that means the TF command can also uh, grab or take into input the state matrices. And that goes the same with the factored form using the ZPK command. Applying this to the exercise, so from here, we can see that the TSSE, which represents again the state space of these four matrices, will result in the following. Now, the approach for this one is different because by using this initial method of converting from state space to transfer function, there are extra numbers in the numerator. So to demonstrate, I will use the TF command directly. So here I am using the TF command directly, and you can notice from this one, there are extra numbers in the e raised to negative 14 and negative 15. Although they are present, they shouldn't because they are approaching zero. So that means they are too small or insignificant to be considered for this equation. So to fix this, instead of using the TF command directly, first I will grab the numerator and denominator data from the state space representation using TF data. So this will result in the numerator and denominator of your transfer function. So to do that, you can see here these are the coefficients for that. Then I will use a self function command that will filter out values that are lesser than 1 e raised to negative 7. these are considered too small. And so by running these, you can see that for the final transfer function, removing these three values, we get the following. This is more accurate and it displays the expected output correctly. However, there's another problem which is still not resolved for my case up to this day. So from the polynomial mode, the factored mode can be done by ZPK. However, that means this is as an input. And so when this is directly plugged here, you can see that it still did not output the correct result to this transfer function. What we can do is use the N and D from the TF data to convert this into the zero pole using the TF to ZP command. And then using those coefficients, or rather those matrices, to then the ZPK command with 4 as its gain, as obviously from this result. However, this resulted in the same result. And I think the reason for this one is because in the TF command from the state space representation, this is already saved as a result. And thus, by using this self function or formatting though, since it still uses this N and D from the state space, it is saved as a hidden result. So it's not filtered when you now consider it here in the TF to ZP command. And thus it resulted in the same output as the original. And so for the transfer function to state space, first we have the numerator and denominator. We convert this into transfer function using S as the TF. And then we can convert this back into the original using the TF to SS. This results in the canonical form by default. But again, there is a direct conversion to the phase variable form using the following lines of command, which was straightforward. So in conclusion, MATLAB has a way of expressing your transfer function in state space and likewise state space in terms of the transfer function. Notice that converting a transfer function to state space puts it in a matrix which is similar to putting it in the digital world instead of the analog counterpart. So with that, the digital space means that you can quantify it per point, you can plot this discretely, and in discrete control systems, this is particularly useful. So with that out of the way, another mention is again the usage of the command SS from the transfer function will result in some inaccuracies. Likewise, that is also the same when you convert from the state space to the transfer function directly using the TF command. So that concludes my report.